Hey everybody, today we're going to look at graphing skills. Since the relationship between two variables in an equation can be represented by a graph, then it would behoove us, and if you don't know what that word means, look it up, to remember our graphing skills. Graphs are very important in physics, so we're going to be taking quite a look at graphing skills. Now, when you are graphing variables for a given relationship, we have to know which one goes on the x-axis and which one goes on the y-axis. So that means we have to know how to determine what variable is which in an experiment. Let's start with the independent variable. Independent variable. The independent variable in an experiment is the variable that has values which are chosen by the experimenter to be certain values. For example, you might choose an amount of force to push an object, 5, 10, 15, 20, 25 newtons. You're choosing the amount of force. The independent variable for which you've chosen the values is always plotted on the x-axis of the graph, okay? So the ones you choose go along the bottom of the graph. The other variable depends on the values that you've chosen for the independent variable. So the dependent variable depends on what you let the independent variable values be. So if you chose forces of 5, 10, 15, 20, and 25 newtons, how does that affect the acceleration of the object you're pushing? So the independent variable you choose values for, convenient values, it goes on the x-axis. The dependent variable is what you would measure, and that goes on the y-axis. It is affected or changes as the independent variable changes. Now, a good example is looking at a spring. A spring is a little device. Well, let me show you one. Okay, so here's an example of a spring. All right, see, boingy, 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 boingy. I like springs. Springs are cool, okay? So anyway, I want you to notice that on this spring, in order to take the length of the spring and stretch it to a new length, you have to apply a force, okay? Now, look at this example right here. It says, if you want to see how much force it takes to stretch a spring, you could choose values for the stretched lengths. For example, I might fix one end of the spring and then pull the other spring until it's 2 centimeters longer than it was, 4 centimeters longer, 6, 8, 10, 12, whatever, okay? And I could see the amount of stretch the spring goes through. Then I could measure the amount of force it took to pull the spring to those particular stretch values. That would make the force the dependent variable because it depended on the value of the stretch I wanted. So I would plot the force as the dependent variable on the y-axis and the stretch that I chose on the x-axis because the stretch, since I chose it, would be independent. Now, if we're going to graph that, then there are some requirements that I absolutely make all my students abide by when it comes to graphing. And you better pay close attention because this is what I require all year long. Item number 1, all graphs must be on real, honest-to-goodness graph paper. Okay, you do not get to take a sheet of notebook paper and draw a little squiggly line down the pink one and another squiggly line along a blue one. That's not a graph. Okay, that's a sketch, but it's not a graph. So you must use real graph paper. Secondly, all graphs must have a meaningful title. That is a title that in some way tells you what the physical phenomenon the graph represents is. You cannot say F versus X, which is force versus stretch. You cannot say X versus Y. That won't cut it. It needs to say something about the physical phenomenon being represented. So let's take a look. We're going to actually do a graph. And right here, if we're going to do a graph on the force needed for spring stretch, then that would be an excellent title. So on my paper, and you have this page with your notes also, I'm going to come over here to this blank graph grid that I have attached into your document, and we're going to put the title on: Force Needed for Spring Stretch. See, I even have some data ready for us. Data that I created. Okay, so we're going to be doing our graph to plot this data right here. Okay, now let's go back and see what else we need. Thirdly, we need a ruler or a straight edge in order to draw axes. We do not freehand axes because humans cannot draw a perfectly straight line. And if you want to look like an intelligent individual when you go to university, you'll use a straight edge. Okay, if they're not using some sort of a graphing program, you have to graph it, you better use a straight edge. So that's what I'm going to do right here. And it doesn't really matter if you start on the side or inside a little, but we're going to use the whole grid. Do not, if you have a big grid space like this, do not put a little tiny axis up here in one corner. That won't cut it either. So here we go. I'm going to draw a line down this side using my straight edge, and a nice dark line over here on this side using my straight edge. Boom, just like that. See? All right, down here in the corner, this would be the origin. All right, now what's next for our graph? Now we need to label each axis with both the quantity being measured on that axis and the unit by which we're measuring it. Remember, a given quantity can be measured with a number of different units. You need to make sure you put the correct unit for the quantity you've measured. For our purposes, our two quantities are spring stretch, which is a measure of distance, so it's in meters, and the force is measured in newtons, not dynes. So we have to do that. Now, as we said before, our force is the dependent variable. It depended on the values chosen for the spring stretch. So we're going to put the force over here on this side, and I put the units in brackets. Brackets make it very clear that that is a unit, okay, and not a capital N for north or something. All right, over here we're going to put stretch, and it's measured in meters. Okay? All right, what's next? Next, we're going to choose a convenient scale for each axis according to the data to be plotted. That means you have to look at the range of your data for each axis. Now notice, a scale does not have to be the same for each axis, but each square along an axis must represent the same increment of measure. In other words, if you're going to let each square represent a value of 1, you're going to go 1, 2, 3, 4. You can't go 1, 2, 5, 6, 8, 9. That doesn't cut it, okay? You have to actually adhere to a scale for each square. Now, does that mean you have to put a number on each square? No, you don't. So let's take a look. If we look at the data for the stretch, okay, the data for the stretch, we're going from about 0 to about 0.2 0.2. I would call that our range, 0 to 0.2. So I'm going to come down here and I'm going to look and say, oh look, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9. Of course, it would be short 1. Well, that would be 40. So I tell you what, let's just go from the first 20, and I'm going to let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is going to be 0.1. All right? So halfway in between is going to be 0.05. All right, so each of these is 0.01, 0.01, 0.02, 0.03, 0.04, 0.05, till we get it to 0.1. All right, now another 10 squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is going to be 0.2. So halfway between is going to be 0.15. Okay? And we really don't need to go any further because our data stops right there. Now, let's take a look at the y-axis. We're going to go from about 0 to about 2.5 or say 3. All right? So we want to stretch that out a little bit. Okay? Always stretch it out because if you make it real small down here, you're not going to get a graph that looks like anything. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll make that 1.0. All right? And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to make that 2.0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There, that'd be 3.0. Okay. So, the scales are different. We did use one increment for each square, but here each square is 0.01. Here each square is 0.1. Okay? So they are different squares or different scales. Now we're ready to see what's next. It says carefully, and this should say plot the data using small pencil dots which need to be circled. Okay? That's because, guys, and let me use a corner up here. This right here is not a data point. That is a whole conglomeration of data points. That is very bad science. You don't know where the exact data point is. It could be halfway down here, which is a different value, or up here, which is a different value, or over here, or over here. Guys, don't make big blobs. Those are incorrect. So you make a small dot, and then we're going to circle it so that we know where it is. So our first data point is 0.01 over and 0.5 up. So 0.01, and halfway to the 1, we make a small dot right there and circle it. Okay, just like that. The next one, number 2, is going to be 0.05 over and 1.1 up. So we're just a line above the 1 and halfway from 0 to 0.1 there. Okay, circle that one. Next is 0.09 and 1.5. Well, here's 0.09 and 1.5 would be 1, 2, 3, 4, 5 would be right there. So put a little dot right there. Whoop, there we go. All right, and the fourth one would be 0.14, which would be right before 0.15, and 1.9 up. So we need to go up to the 1. Whoops, there's the 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're right below the 2 mark. All right, make your little pencil dot right there and circle it. And the last one, 0.18 and 2.5. So 0.18 would be, here, this is 0.19, 0.18, and we're going to follow it up to 2.5. Oh, here's the, let's see, here's the 2. So 1, 2, 3, 4, 5. Okay, right there. We make a pencil dot, a tiny little pencil dot, and we circle it. All right, so there's our data points. Okay, that looks pretty good. Now, what relationship would you say this is? I would say it's linear. Okay, so next, what are we going to do with these data points? All right, here we go. It says if the relationship is a linear one, then what we're going to do is we're going to use a straight edge, a ruler again. And we're going to use it to draw the best fit straight line. We do not freehand a linear graph. That is a huge no-no in science. Okay? That is a huge no-no. So we have to use a straight edge to do this. Now, this is the reason I like these transparent rulers, because if you plop them down on top of the points, you can still see the points through the ruler. And what you want to do to draw the best fit is find the line that averages the points. Are all the points going to be on the line? No, they shouldn't be, because there's error involved in all measurements. But they can be pretty close. So I'm just going to take my ruler and move it up through here until it looks like the edge is about halfway between all the points from this way, from side to side like this. In fact, when I do, I can see I've got 2 that are slightly below the edge of the ruler and 1, 2, 3 slightly above the edge of the ruler. That looks pretty good to me, actually. Oops, I moved it. All right, so I'm going to draw right along that edge, and look at that. Isn't that lovely? Now, if you want to extrapolate all the way back to the y-axis, you can, and see your y-intercept, okay? So, in fact, our y-intercept here would be 1, 2, 3, 4, 0.5. 0.5. Not bad. Now, if we get the slope, we can actually write an equation for this line. In any case, in fact, that's the next thing, but I do want to talk about one thing first. You'll notice there's another blank right here. Let's see what this says. It says, points do not have to all be exactly on the line. The line is the average of the points. Aha! Okay, and it says the distance from the line to each point, that should say to each point. The distance from the line to each point. Let's talk about that a minute, okay? You'll notice each of these points is a certain distance from the line. Some of them are a little closer. That one's really close. Some of them are a little further, all right? But the distance between the point and the line, this distance is actually something we've talked about before, believe it or not, okay? You want to know what it is? All right, watch this. I'm going to just flip over and put it right here. Watch this. What did we say this was in our study of error? This is the deviation. This is how far any single measure is from the average of the measures, right? Well, look. How far any single measure is from the average of the measures. So this space is the deviation of that point. Every one of these points has its own deviation. Isn't that kind of slick? All right, so now, continuing on, let's see what else we're going to do. Oh, let's write that down, deviation. All right, so now we know, deviation. If it's a linear graph like this one, you can also determine the slope of the line, because in physics, slopes have physical meanings, or at least most of them do. So how do we accurately find the slope of a given line? And this is where most people fail, because they don't pay attention to what I'm saying. Whenever you're going to find a slope of the line, you must choose 2 new points on the line of best fit. not data points. We never, never, never use data points to find the slope. Why do we never use data points to find the slope? Because they have error involved. So what we do is we're going to choose 2 new points on the line, okay? All right? And watch this. I like to choose points where the line goes through the crosshairs, as I like to call it, like right here. Look how the line comes up and it goes right through where these 2 cross, which makes that a very convenient point to use because I know the X value and I know the Y value, okay? In fact, let's write them down. So the X value for this point is 0.17, 0.17 meters, and the Y value is 2.3 meters. All right, let's find one more. You have to have 2 points to find a slope. So let's look for another point that goes right through the crosshairs. And ooh, I found one way down here. In fact, guys, the closer together your points are, that's not as good as if you can find 2 points that are further apart. So I'm going to use this one where the y-intercept is. Oops, the red doesn't want to, it just smearing the blue. We're going to use that one right there. And that would be 0.5, that would be 0, no x, all right? And then we go up 0.5 newtons. Oh, and this was supposed to be newtons, not meters. Okay, I got it fixed now. Newtons, meters, newtons, meters, newtons, meters, newtons. Okay, so now we have our 2 points. Notice I did them in red. Why would I do that? To distinguish them as the slope points as opposed to the data points. Now, quickly, we go back here. If you'll remember to calculate slope, you're going to take the 2 points that we've just found and use the slope formula. y2 minus y1 over x2 minus x1. Y's over x's. The most common boo-boo I see here is people accidentally getting them reversed. So right here, we're going to say y2 minus y1, 2.3 minus 0.5, okay? Let's just do it right down here. So the slope here, y2 minus y1 over x2 minus x1, that's going to be 2.3 newtons minus 0.5 newtons. And yes, the units make a difference. All right, and we're going to divide that by the x values, which would be 0.17 meters minus 0. Okay? All right, so now we're going to subtract. I get 1.8 newtons on top, and I get 0.17 meters on the bottom. Okay, now are we done? No, because in physics this means nothing. All that is a ratio. It doesn't physically mean anything for us yet. We never leave slopes in ratio form in physics. Have you ever seen a measuring device that measures ratios like this? Of course not. So we don't use them on slopes either. Now, I know they teach you to leave them in ratio form in math class, but math class is not physics. So we're going to divide 1.8 by 0.17. And the value I get, if we round to 2 sig figs, is 11 newtons per meter. Here's what that means for us. This is saying that to stretch the spring 1 entire meter, you would need 11 newtons of force. 11 newtons per meter of stretch. That has physical meaning. That we can understand. This makes no sense. So always divide out your slope, okay? All right. I think that's it for now. Thanks for listening.